Organophosphates are awesome. They're commonly used in herbicides, pesticides, a lot of things that are really helpful for us in society. But sometimes they are not used in helpful ways. In fact, sometimes they're used by people with ill intent. In 1995, in Tokyo, Japan, 5 men stepped onto a subway station and placed small plastic bags in strategic locations. Now, inside of each of these plastic bags was a type of organophosphate called sarin gas. Sarin gas was invented by the Nazis in the 1930s, but was actually never used by them. However, this day in Tokyo, Japan, it was. Each of these men belonged to a cult that was set on accomplishing their doomsday agenda. They each carried a pointed umbrella with which they poked these small bags containing sarin gas. They immediately left the subway, but those that were unaware of what was going on in the subway, within a few seconds, those thousands of people felt stinging sensations in their eyes and felt nauseated, as sarin gas is really good at making the parasympathetic nervous system fire off. Now, this was the beginning of what would result in one of the biggest terrorist attacks in Japan's history, as it killed 13 people and wounded over 5,000. The crazy thing about this is that this wasn't the last time organophosphates or even sarin gas has been used in harmful ways. It's still a problem that we face from terrorists or our military faces. It's still an issue. And so we did an experiment that helps us to see what can be done about this. But before we jump into our experiment, we first need to understand what exactly, on a small level, does sarin gas and other organophosphates do to our bodies.
Cool. Thanks, Jaden. So the physiology behind organophosphates. Now, as Jaden said, we find them in common household things like pesticides. We use them every day. But what happens when they go wrong? What happens when they get inhaled? What happens when we accidentally leave them down and our children get them? Or they're used against our soldiers just to be used? Well, to see that, we need to go down to a cellular level. Now, specifically, these organophosphates, they target what we call the neuromuscular junction, as many of you are pretty familiar with. Specifically, what they target an enzyme called acetylcholine esterase. Now, acetylcholine esterase's job is to go throughout and break down a neurotransmitter called acetylcholine. When we have increased amounts of acetylcholine, we have increased stimulation, which means we have muscle contraction. Now, acetylcholine esterase, which is supposed to break it down, if that gets shut off, well, hopefully we can start to see where the problem lies. We get spastic muscle contractions, at least eventually leading to flaccid paralysis, and that can really be a problem. So what exactly does it do to acetylcholine esterase, though? So with acetylcholine esterase, as it goes about its day, just breaking down acetylcholine, a organophosphate will eventually find it and bind to it, rendering it inhibited. Now, that's not all bad because, again, in small amounts, if just a few enzymes get inhibited, it's no big deal. However, in larger amounts, the more that we have built up, the more organophosphates within a cell, the more likely we are to have what we call aged acetylcholine. Now, aged acetylcholine we can see up here on the top of the screen. Just going to circle it really quick. Now, what makes this so dangerous compared to just our regular inhibited is that it's been hydrolyzed. Our little R group representing that occurring leaves, and now the acetylcholine is essentially stuck. It's stuck in a new form and it can't do anything with acetylcholine. Now, with normal inhibited acetylcholine esterase, we do have the opportunity for it to be broken down and we can regenerate and eventually return where we start again. However, it depends on what levels of organophosphates do we have within our body at that time and where are they affecting us the most. So with this graph, just a really quick go over it before we get into our data points. The total amount of organophosphate inside represented by the y-axis and our exposure time on the x. Now, we have two different kinds we tested. 14C-MPS exposure represents our normal organophosphate after binding to acetylcholine esterase, while 14C-MPO represents our converted organophosphate into what we call an oxon, and more on that later. As we can see here in our graph, the square boxes represents our MPO exposure, which is a lot higher as time goes on, meaning that in higher concentrations, we have more oxons being created and more acetylcholine esterase being shut down. This, as we have been discussing, would be detrimental to any human. And that's why we deem this study so important, so that we can prevent this.
Thanks, Logan. So now we're going to get into what we're testing and why it's important. Just briefly explaining the different types of pesticides or organophosphates that we're going to be using is an image here that breaks down the difference between a normal organophosphate here on the left and its oxon on the right. We're going to be using both of these toxins because they're both present in an organic system. The difference being the sulfur group seen on the left is replaced by a double bonded oxygen, which, as Logan described, is extremely hard for the body to deal with. So to understand what the body does to combat these toxins, we wanted to look at a specific gene. This gene is called PON1, which is responsible for the production of an enzyme called serum peroxidase. This enzyme breaks down organophosphates and can handle small amounts of organophosphates inside the body. Knowing that this is a defense system, we needed to understand just how significant this is. So we designed two different mice to study these effects. The way we designed these mice was using gene targeting methods. What we did was we knocked out the PON1 gene, which is responsible for that previously mentioned enzyme. We hypothesized that when we remove this enzyme, we are going to see different effects in how the body can deal with organophosphates. Our two study groups include the minus genotype mice, depicted in the bottom left by the gray mice. This mice, or this population of mice, is a group that has no PON1 gene. So these mice are unable to respond to organophosphates because they have no ability to break down the organophosphates, which attack acetylcholine esterase. And to include a control group in this study, we included the plus genotype mice, which is the wild type or an unmodified mouse. This mouse has normal amounts of acetylcholine esterase, and we need both groups so we can understand exactly what organophosphates are doing. Now, before we decided to inject these mice with toxins, we wanted to get a baseline level of how much of this enzyme is present in the mice. So we have the peroxidase and its counterpart, the chlorpyrifos oxidase, which breaks down the oxon. And the data on the left in table A, we can see how much peroxidase activity is represented in each mice population. The plus population has a substantial amount more of this enzyme. And the minus genotype, the modified mice that we created, has almost no activity of peroxidase. What this means is we successfully destroyed the gene that is producing the enzyme or responsible for the production of the peroxidase. Similarly, in dataset B, we're looking at the plus mice versus the minus mice. Once again, the unmodified mice have normal levels of this enzyme, and the minus mice is almost completely inhibited. So from this, we can gather that we successfully targeted this enzyme, so there's almost no defense system for the mice. Now that we understand what our populations of mice are capable of, we wanted to see the effects of introducing a toxin to their system. The first toxin we introduced was the oxon, which is harder for the body to deal with. In dataset C, we wanted to measure the concentration of acetylcholine esterase activity in the brain. So on our y-axis here, we're observing how much acetylcholine esterase is working. And on the x-axis, we're looking at the quantity of toxin introduced to the mouse. Designated by the circle and square on the line, we can see which population is being affected. On the top here, we're looking at the wild type mice. These mice are unaffected with the enzyme, so they have normal quantities of the enzyme able to break down acetylcholine, or able to make acetylcholine esterase, which means acetylcholine esterase is higher. It's present in greater quantities compared to our modified mice down here, much closer to the x-axis. This means that there's much less acetylcholine esterase and there's much less ability to break down these organophosphates. Similarly, in dataset D, in the diaphragm, the information is almost the same. The unaffected mice, the plus or the wild type mice, have almost normal levels of acetylcholine esterase activity, and the modified mice, minus, seen by the circles, are having a hard time developing enough acetylcholine esterase. So they're very susceptible to the effects of organophosphates. Continuing on, we wanted to measure a different toxin, the chloropyrifos, which is not as dangerous as the oxon, but still can have adverse effects on the body. Just as we saw with the previous data, the normal type mice, designated by the white column, is much more able to produce acetylcholine esterase than the minus type, showing us that, once again, the mice that had this gene removed from them are having a hard time breaking down organophosphates because of the removal of this defense mechanism.
So to conclude and to summarize what we learned from our study, mice lacking the PON1 enzyme were much more susceptible to the effects of organophosphates than those that still had the PON1 enzyme. So this begs the question, why do we care? What does it matter to us whether mice can break down organophosphates or not? And the simple answer is, it's because people matter. We don't care about mice, but we do care about the information derived from doing these tests on them, seeing that it could benefit the human race, because it just so happens that humans also possess the PON1 gene, which means we're able to break down organophosphates in small amounts too. So if we can use the information regarding the PON1 enzyme to somehow create a supplement or a vaccine to enhance PON1 expression in humans, then it could be a real game changer. In fact, there have been other studies done and researching this exact idea to see whether it's feasible or not to enhance the PON1 enzyme. And so in this study, the researchers took a bunch of mice. On the most left two groups showed the normal amount of acetylcholine esterase in mice brains. And then from that, they took two groups of mice, one possessing normal amounts of PON1 enzyme, and that's shown by the middle column. And then they took two other groups and they enhanced the PON1 enzyme in those mice, and that's shown by the farthest right two groups. And then they injected both groups of these mice with organophosphates, and then after a couple of days, they harvested the brains and were able to measure the amount of acetylcholine esterase activity. And you can see that in the two groups to the right, it's obvious that they were a lot more protected from the effects of organophosphates just because they had more of the PON1 enzyme. So from this study, we learned that there is some validity to the idea that we can enhance the PON1 enzyme and it could protect humans. Like Jaden said at the beginning, there are people out there who will go to extreme measures to cause harm to others, whether it be through a bomb or through sarin gas, like an example he gave earlier. If we could enhance the PON1 enzyme and cause immunity or near immunity to certain groups of people, then we would effectively be removing one of the weapons from their arsenal. On a much larger scale, we know that organophosphates have been used in war. And if in the same idea, if we can make a supplement or a vaccine and enhance the PON1 enzyme expression, then it might just give us just enough of an edge in a future war to bring more of our soldiers home unharmed. So how close are we to making these possibilities realities? Well, we know from the study that PO11 enzyme expression works in mice, but there are some ethical setbacks when it comes to testing this on humans. So while we do have some evidence, it's going to be quite a while before we're able to apply this science to humans. But we are making progress, and we are hopeful that that one day, with the help of this science, many of the problems that we see in the world regarding organophosphates can be solved. Thank you.